So, carrying on with Module 9, and today we are doing lesson 9.3. And so, as you can see, heading theoretical probability of simple events, and that is our lesson. The learning target, I can find the theoretical probability of a simple event and its complement and understand the relationship between them. Okay. So there are several vocabulary words we are going to learn in this lesson. Complementary event, sample space, theoretical probability, and uniform probability model. So these are the words we are going to talk about. So let's start with what is a sample space. So I've just given an example of a number cube over here. So in a probability experiment, the set of all possible outcomes is called the sample space. Okay, so all possible outcomes is called the sample space. And to find the sample space of a simple event, you can make a list of each unique outcome. Okay, so when rolling a number cube once, the sample space is the outcome of each face. So that's what I've written over here. As you can see, whenever I'm rolling a number cube, my outcomes will normally, the cube has six faces. So the outcome would be any of these that it can land on when I am rolling a number cube. And suppose you rolled a number cube 10 times and recorded the results like I have over here. Okay. So I have rolled the number cube, and this is what I get. One was rolled 0 times, two has been rolled 3 times, three 2 times, 4 1, 5 4 times, 6 0 times. Okay. So if I count up 3 plus 2 plus 1 plus 4, that gives me 10. So that's telling me I have rolled it 10 different times. Okay. Now, when I look at this, even though, the sample space in this case, we can see the relative frequency ratios of rolling a 1 or a 6 are what? It is 0, right? They are both 0 on 6 if I'm taking these rolls. Okay. So, yeah. And it doesn't matter because neither of those numbers were rolled when I was, rolling a number cube. And so, as you can see, the relative frequency ratios of rolling a 1 or rolling a 6 are both 0 on 6 or 0 because neither of those numbers were rolled. And the sample space is still 1, 2, 3, 4, 5, 6. That is still my sample space. Okay. Even though rolling a 1 or a 6 did not happen, because all possible outcomes are included in the sample space, all possible outcomes. Okay. Now, the sample space is not dependent upon actual results because each new time you roll the number cube, there are 6 possible outcomes. Okay. So please remember, the sample space is not dependent on the actual results of when I rolled the number cube. Okay. Because anything is possible when I am rolling it. Now, let's say, you have to find the sample space. Let me take you to the board. I can give you the question. So let's say this is my question. Okay. Each letter in the word mathematics is written on a piece of paper and placed into a bag. A letter is drawn at random. What is the sample space? Okay. So I'm looking at this and I'm thinking the sample space is the set of all unique possible outcomes. And in this example, because some letters are repeating, the outcomes in the sample space are each unique letter that appears in the word. And you basically are going to take each of these letters and you are going to record them once. Okay, so if I look at mathematics, all right, what is the sample space? The sample space I'm looking at each of the letters. I'm going to record them only one. T, H, E. M is already done. T is already done. I, C, and S. So if I'm looking at this, my sample space of the letters is going to be M, A, T, H, E, okay, I, C, and S. Okay, so the sample space consists of the unique letters of the word mathematics, and each unique letter is listed only once. Okay, so as I can see, whatever I've underlined, because these are repeated, so I am not going to list them two times. I'm just going to list the letters just once, and this is actually my sample space. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is my sample space of when I have mathematics listed. Let's look at another example. And if I say, in a 7th grade math class, there are 5 students with blue eyes, okay, 4 students with hazel eyes, and 2 students with green eyes. One student is selected at random. What is the sample space for eye color? So eye color, okay? So we have blue eyes, we have green eyes, we have hazel eyes. So those are my eye colors. So it would be, my sample space would be blue, hazel, and green. Okay, so eye colors would be blue, hazel, and green, because the sample space, it's basically you're writing it just once. We're not talking about 5 students or 2 students or 1 student. We are talking about the eye color. So since those are the 3 colors that are there, those are going to be written one time, and that would be my sample space. Okay, now let's quickly talk about theoretical probability of simple events. Okay, let's talk about theoretical probability of simple events. And experiments, such as rolling a number cube, or tossing a coin, in which all of the outcomes are equally likely, are known as uniform probability models. Okay, so uniform probability models, when everything is equally likely, equally likely. Okay, in the uniform probability model. So if I say theoretical probability, this is based on uniform probability, or what should happen in a probability experiment. Okay, so what should happen in a probability experiment. So if I'm talking about the ratio of this, probability of an event, we're talking about theoretical probability. Okay, so this is equal to number of favorable outcomes, number of favorable outcomes, okay, so number of favorable outcomes over total number of outcomes, over total number of outcomes. All right, so whenever we're talking about theoretical probability, it is nothing but the ratio of the number of favorable outcomes to the total number of outcomes. And so I've just drawn a probability number line just to show you, since we have done this in the first lesson when we did lesson 9.1. So I've just drawn a number line just for you to see, when it is impossible, when it's unlikely, equally likely, likely, or certain. So it kind of corresponds with each likelihood. So, 0% would be impossible. If it's just about 25% or one fourth, then it is unlikely because, the probability of something else happening is higher. If it's like 50-50, then it is equally likely. And if it has a majority, like 75%, it is likely. And if it's like completely that, the entire pie chart or something, for example, or circle graph is, let's say you're spinning a three and all of them have only three, so then that's 100% possibility of it actually happening. So it is certain. So this is a probability number line that I just wanted to show you. And let's say, suppose you tossed a coin 20 times and recorded the results. Okay, let's say you toss a coin 20 times. So 20 times coin toss. Okay, and let's say when you tossed it, you got a table like this. And we know that we just have in a coin, what do we have? We just have heads or we have tails, right? So here's my outcome and here's my frequency. That's how many times did it happen. Okay, and so let's say heads and tails. Okay, so let's say heads, when I tossed it, I got 17 heads and I got 3 tails. Okay, so the relative frequency ratio of tossing heads in this case, when what happened, this was what? 17/20. And the relative frequency of tossing the tails in this case was 3/20. All right, and yeah, and then we can calculate the percent of that. Okay, now because each outcome when tossing a coin is equally likely to happen or not happen, normally that is actually one half, because either you can toss heads or you can toss tails. Okay, so therefore each outcome when tossing a coin is equally likely to happen as not to happen. So the theoretical probability of tossing heads is one half, and the theoretical probability of tossing tails is also one half, because you just have heads or tails. All right. Now, why are the relative frequency ratios so different from the theoretical probabilities? Because what is a theoretical probability? It's basically what you can expect when you are tossing a coin. All right. So theoretical probability is what you should expect when conducting an experiment, while the relative frequency ratio describes what actually happened. Okay. So this actually happened. So that is why this is relative frequency. But what is the theoretical probability? It is what you are expecting should happen when conducting an experiment. So that is the difference between the two, what should happen and what actually happens. And that's the difference between theoretical and relative frequency. Okay, now let's do an example where we are taking a sample space of simple, here let's do a theoretical probability of simple events. So here we go. All right, now 8 discs are marked 3, 4, 5, 6, 7, 8, 9, and 10, such that each disc is marked with exactly one of these numbers. A disc is selected from the bag at random. What is the theoretical probability of selecting a disc marked with a prime number on it? Okay, so now when we are going to do this, we are going to look at which ones are the prime numbers over here. Okay, so let's look at the prime numbers. A prime number is one which is only divisible by itself or 1. Okay, so let's look at that. And I can see that my prime numbers here are 3, 5, and 7. All right, so I have 3 prime numbers. The rest of the numbers are composite numbers. So if it's talking about the theoretical probability of selecting a disk marked with the prime number on it, we are going to look at, there are 3 prime numbers, okay? And then I'm going to look at what is the total number of numbers here. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have total of how much? 8. So therefore, the probability of a prime number is equal to, how many prime numbers did I have? 1, 2, 3. Right? So 3 prime numbers out of a total outcome of 8, which is the sample space. All right? So when I look at this, I'm then going to simplify this. Now I can, do a couple of things. If I have 3/8 and then I am simplifying, well, the fraction is in the simplest form. But if I am going to see the percent of this, all I do is I can take 3 and divide it by 8. Decimal goes behind the whole number, decimal above decimal. Okay, so 0 times 8 is 0. I get 3. Annex a 0, bring it down. Okay, and then I have 3 times 8 is 24. And 10 minus 4 is 6. Annex a 0, bring it down. All right, 7 times 8 is 56, and I get 4. Annex a 0, bring this down. 5 times 8 is 40, which is 0. So I can get 375,000th as a decimal. But if I change this to a percent, because this is 375,000th, and a percent has to have a denominator of 100. So whenever I have a decimal, I just move it 2 places to the right, and this would be 37.5%. Okay, 37.5%. So the theoretical probability that a disk with a prime number on it is selected is 3/8, 375,000th, or 37.5%. Okay. Now, let's quickly discuss what is a complement of an event. Okay, so suppose you are rolling a number cube, all right, and the desired outcome is an even number. Okay, so a success would be defined as rolling an even number. Okay, so you are rolling a number cube. Okay, so you're rolling a number cube, and the desired outcome is an even number. So number cube, and you want an even number. Okay, you want an even number. So we know that when we are rolling a number cube, we have what? 6 different numbers on the number cube. What is success in this case? Success would be if I rolled an even number. Okay, so if I rolled an even number, that would be a success. All right, and rolling an odd number is not a success. All right, so what is not a success? Not a success would be if you rolled an odd number, which is because that is the opposite of what you wanted, right? Because you wanted an even number, so that would be a success. And opposite of that, what you did not want would be the odd numbers, okay? So these 2 events are known as complementary events. These are known as complementary events, okay? These are complementary events. Now, the sum basically, because they cannot happen at the same time. All right. So if you're trying to roll an even number, you cannot roll an even and an odd number on the same number cube at one time. Okay. So these are complementary events because they cannot happen at the same time. So once again, what are complementary events? Complementary events are two events in which either one or the other must happen, but they cannot happen at the same time. And the sum of the probability of an event and its complement is 1 or 100%. Okay? And so if you're writing an equation for this basically means what? This means the sum of an event actually happening, let's say A, all right, and it's, which is not A, for example, I'm just giving an equation, plus probability of not A, all right, also written as this. Okay, the sum of this is equal to 1. All right, so let's consider the following scenario. Okay, let's consider the following scenario. You roll a number cube. The desired outcome is a 3. Okay, so you roll a number cube and the desired outcome is we want 3. Okay, now if I'm looking at 3, the complement of the event is not rolling a 3. Okay, so you want 3, and the complement would be not rolling a 3, right? Because it's the opposite, not rolling a 3, which would be you're not successful. Okay, so when you're not rolling a 3, what are those? 1, 2, 3 is already rolled. 4, 5, 6. So those are the other numbers you can actually roll, which are a complement of 3. So we're going to notice a relationship between the probabilities of an event and its complement. So if I take probability of rolling a 3, we put the total outcome of rolling a dice that or number cube is 6, right? And how many 3s do I have in that? 1. So this 1, 6 is my actual, there's one number 3 and a total of 6 numbers on the number cube. And then the probability of not rolling a 3, how many numbers are that? 1, 2, 3, 4, 5 out of 6. Okay, and so when you were talking about the sum of the probabilities of what you want to roll and its complement is actually going to equal 1, this is what it means. If I take the sum of these two, this one and these two, look at this. All right, I have 6 denominator, 5 plus 1 is what? 6. And what is 6 over 6? I get 1 whole. And that's basically what I was trying to explain earlier, that when you take the probability of an event and then the complement of the event and you take the sum of these two, you are going to get 1 as your answer. Okay, so let's quickly talk about another one. You spin a spinner that is divided into 8 equal size sections numbered 1 through 8. The desired outcome is an even number. Okay, so now I'm taking a spinner with 8 even sides or 8 equal size sections. Okay, so my desired outcome is an even number. So if I have 1, 2, 3, 4, 5, 6, 7, 8 in that spinner, if my desired outcome, which is even, okay, even is how much? 2, 4, 6, 8, right? So that is how much? 4 out of 8. Total is, because 1, 2, you got 8, right? And then if I have probability of not even, because that is the complement, how many do I have that are not even? 1, 3, 5, 7. So I'm just going to circle the not even ones. And that is how many numbers? Again, 4 out of 8. And if I add these two, what is 4/8 plus 4/8? I get 8 over 8, which is 1 whole again. So that's basically what this is, okay? Whenever you take the complement with, the number that you have, the success rate, and the not success rate that we wanted, when you add them up, you definitely are going to end up with a 1 as your answer. Now, uh, real quick, let's find some complements based on this. Okay. Question that I'm about to put up. All right. So let's look at this one. All right. Find complements of simple events. So in this, let's look at that question. All right. Raphael is going to ride a roller coaster chosen at random and wants to find the probability of choosing a roller coaster with a height less than 250 feet. What is the probability of the complement of the event? Okay, so complement is, remember, what we want, the opposite of that. Okay, so Raphael wants what? She wants to ride roller coaster at the product choosing a height less than 250. So that is the first thing let's look at. Okay, we want a less than 250, but what does the complement mean? Complement mean is going to be the opposite of less than 250. So we've got to find the numbers which are more than 250, because that is what the complement would be. Okay, so more than 250, I have this, this one, and this one. Okay, so as I can see, we are going to identify the complement of the event, and then we are going to list all the outcomes that make up the event's complement. And these are the roller coasters with a height not less than 250 feet. In other words, you find the roller coaster with a height greater than or equal to 250 feet. And so those roller coasters are Thunder Dragon, Screaming Spider, Flying Eagle, Twister Wave, Triple Tornado. All of these roller coasters have a height which is greater than 250. And these are 5 outcomes that make up the complement. So to find the probability of the complement, that means probability. Okay, we're trying to find the complement, so which is not less than the opposite of what it's asking, not less than 250 feet is going to equal, all right, number of outcomes in the complement over number of total outcomes. So what were the outcomes? 1, 2, 3, 4, 5 of them were the complement. So 5 over total amount. 1, 2, 3, 4, 5, 6, 7, 8 over 8. Okay, so there are 5 outcomes in the complement, so therefore probability of complements is 5 to 8. Okay, and this is the same as saying the probability of choosing a roller coaster with a height greater than or equal to 250 feet is 5 over 8. Okay, now let's do one last problem to understand complements. Here we go. So, all right, a bag contains 25 marbles, 10 of which are red. The other marbles are blue or green. A marble is selected at random. What is the probability of drawing a marble that is not red? Okay, so basically, again, what are we trying to do? we are trying to find complementary events. Okay, so let's do it this way. We can check how many marbles overall. We have 25. Okay, so total outcome goes here. All right, first I'm just doing what is the probability of red. Okay, so this is probability of red. Okay, and how many red do I have? I have 10. Right, so if probability of red is 10, what is the probability of not red? Now we can do it a couple of ways. We can do 25 minus 10. I get 15 over 25. Right, so probability of not red, because that's what the complement is, would be 25 minus 10, and that gives me 15 over 25, because that's what the complement is. And then I am just going to change this to a percent. So if I change this to a percent, I know my denominator needs to be 100, right? So 25 times 4 gives me 100. 15 times 4 gives me 60. All right, so therefore this is 60%, or we can also say it is 60/100. So that is what my probability is of not red. Okay, so basically that's what this lesson is all about. Please remember the difference between a theoretical probability, when we are comparing it to relative frequency. So there's a big difference between, what actually happens and what we are expecting to happen. The complementary events are definitely the opposite of what we want to happen. And so that's what this lesson is all about: theoretical probability of simple events. All right, have a fabulous day, everyone.